Another force that will come up in a course like this has to do with springs. Now, springs are just what you might expect. They're the things that form the suspension in your car or a slinky or anything that sort of pops back when you let go of it. And that popping back is exactly the nature of the spring force. So when you look at a spring, there's just a couple of things to identify on the spring. The first thing that we'll usually encounter in this class here is that springs are always going to have a fixed end. Fixed end like that. So an end that doesn't move. It's always tied to something like a wall or a point like that. It doesn't move. There are problems where springs are free on both ends, but you'll have to take maybe a more advanced physics course for that. It's not necessary for us. We can get plenty of action out of a spring that's attached to one end. Then, of course, you have the spring itself here, which is often drawn like a coil like this. And the defining characteristic of a spring is its spring constant, K. So K here is referred to as the spring constant. And the spring constant has to do with the stiffness of the spring. So even in the examples of the springs that I just sort of rattled off at the beginning of the video here, you can imagine that different springs have different stiffnesses here. So like a slinky can barely hold its own shape even sitting on a flat table. It has a very low K. A spring in your garage door that makes it easy to open is very, very stiff, and there's even warning signs that you can die if you try to adjust them yourself and you don't do it properly. They have very high Ks, so they can spring back very quickly and maybe hit you or something. Likewise, the coils in your car that form the suspension have a very large K, but then the spring, say, in a toaster that makes your toast pop up when it's done doesn't have a very large K. So there's all kinds of Ks and stuff, but that's sort of the defining characteristic of the spring is its stiffness, K. And the last thing that spring has here is the free end. And the free end here is where all the action is going to be because that's the end that can move. Now, here's the crux about springs. When they're just sitting in a most relaxed state like this, say I've just set it on a table, the free end always sort of naturally goes to some position where it's nice and relaxed. This is called the equilibrium position. Equilibrium position of the spring. Again, the free end is just sort of relaxed. It's not pushing or pulling or changing or morphing or anything like that. It's just sort of sitting here in equilibrium. And you can definitely think of this as a spring that's nice and relaxed. That's what the equilibrium position is all about, a nice relaxed spring. Now, here's where the action comes from. Suppose I took this free end of the spring. Remember, this end can't move over here. It's fixed. But suppose I took this free end and I pulled it all the way over to the right like that. And I'll just sort of draw what will happen to the spring. I guess I'll superimpose it here. The spring will start to stretch out. These loops will get all stressed out. And maybe now the free end is clear over there, something like that. So there's the free end now. So what has happened is I've displaced the spring, and the displacement has taken it all the way over to another position over here. I've pulled it this far myself. It's all the way over here. Now what's important about springs is that there's some displacement now. I'll call it delta S. There's some displacement between the equilibrium position of the spring, where it is when it's relaxed, and where we've purposely pulled it to. Now I pulled the spring, but the exact same analysis would hold if I pushed the spring. So if I took the free end and pushed it all the way in this way by some delta S, the same consideration would hold. The spring has been displaced from equilibrium, and that's what's important. Delta S here is always the displacement from equilibrium. How far have you displaced it? So what will happen now is as soon as the spring is displaced from equilibrium, a force will develop on it, and that force then is equal to the spring constant times delta S. This is the spring force law. So you have to ask yourself two questions. Where is the equilibrium position of the spring? How far has it been extended or compressed from that equilibrium position? Multiply the two together, the spring constant times that displacement, that's the spring force. Now, one last thing about the force law is that, as you might imagine, if I took a spring and pulled it this way towards the right, the spring is really going to want to pull me back towards the left. Alternatively, if I took the free end and pushed it towards the left, the spring is going to want to push me back towards the right. So spring forces always sort of oppose the displacement. So you have this displacement from equilibrium here, and what springs do, they always oppose the displacement. They always want to go the other way. They always oppose the displacement. Now, there's one modification to the force law to reflect that. In fact, F is not K delta S, it's always minus K delta S. And this is exactly this opposition that springs always do. So there's the spring law for you right there. You can look it up in your book or on Wikipedia or something like that. This is often called Hooke's law, and it's what governs the behavior of a spring. So there you go, spring force. What is it about? Look at the spring. Hey, where is it in equilibrium? Where is it nice and relaxed, where it's not presenting any force in anything? Note that point. Then you look at, well, how far has it been displaced from equilibrium? Try to measure that, delta S. look up the spring constant. It's maybe given to you in a lot of cases. If you just multiply that displacement times the spring constant with a minus sign, that gives you the force that a spring presents on an object.